Okay, we are now live. So, bom dia a todos. A gente vai começar agora o seminário de hoje da série de seminários da pós-graduação em Física, do Departamento de Física da UFC, né? E hoje a gente vai ter como convidada a Sara Conti, que é uma pesquisadora jovem, vocês devem ver aí como a gente tem colaborado algumas vezes já recentemente, uma pesquisadora e uma amiga aí. I think she doesn't understand what I'm saying now. I'm just telling the students that and the audience that you are young and a young researcher, yeah, and a collaborator. So eu vou apresentar. I'm going to introduce you to the audience in Portuguese, and then I can tell you more or less what I said. Okay. Well, Sara. Yes. Sorry.
Yes.
You understand a little bit? Yeah, I see.
Yes.
Because she's from Italy, ela é da Itália, para quem não sabe, então assim, dá para entender um pouquinho do que eu tô falando. Bom, a Sara, ela terminou o doutorado um doutorado junto entre a Universidade de Antuérpia e a Universidade de Camerino, na Itália, e ela tem colaborado com a gente aqui no UFC em alguns trabalhos juntos que a gente está escrevendo agora, e também com esse grupo FLIT da Austrália, e ela hoje em dia ela é pós-doc, pós-doutoranda na Universidade de Antuérpia, e ela tem recebido vários prêmios por apresentações e posters e tal, tipo melhor pôster e tal, e um dos principais aqui para dizer, então, seria esse que é o Best Invited Talk by Young Investigators, na conferência Superfluidities de 2022, que é justamente a apresentação que ela vai fazer agora, né? Mas, além disso, ela também tinha ganhado já esse prêmio Zonta International Women in Technology Prize e alguns outros prêmios antes, certo? Bom, então, so what I was telling them is about your recent prizes and the fact that this talk was already awarded one prize for like best invited talk, right, by a young investigator. So yes. Please, you can already start. If you, I don't see your screen now anymore.
I'm still sharing.
Oh, it's back now. Okay, yeah, okay. It's back now.
So I can start?
Yes.
Okay. So, bom dia. Hello, everyone. Like Andrea introduced me, so you already know my collaborators. I'm working at this moment at the University of Antwerp, and as he mentioned already, I'm collaborating with the University of Camerino in Italy, and we have this collaboration with this experimental group in Fleet in Australia. And today I would like to share with you one of the most recent work that we have done together. It's on Chester SUPERSOLID of indirect excitons and the phase diagram in double layer system. So it's a long title. I will try to break it in more parts to make clear what we are trying to do. So the first part of my talk will be around the Chester SUPERSOLID. I want to show you what does it mean to have a Chester SUPERSOLID. I want to explain to you why we choose indirect exciton to study this Chester SUPERSOLID. I will give you a bit of background of the phase diagram of these double layer systems that now they attract a lot of attention because of this, of numerous, several investigations done regarding indeed indirect excitons. So let me start. First of all, what is a supersolid? Well, the supersolid is a speculation, is a state that is a bit of speculation that Chester proposed in 1970s, and is exactly what it seems. Is let's imagine that you have a superfluid, and you know that in a superfluid there is a spatial of diagonal long range order. So all the particles, they have the same phase. So there is phase coherence in the system. All the particles, they occupy the same quantum state. And then we go to a totally different system that is a solid, in which every particle has a specific place in the space. There is periodical crystal order, and there is translational symmetry. So what happens when you put them together? Well, you have a supersolid. So you have a state. It's a bit controversial as idea, but you have a state in which every particle maintains crystal order, is positioned in the crystal order, but at the same time they all have the same phase. So it's a coherent state in which every particle has a precise order. So this quite strange state was first proposed in helium-4, in which, again, every single atom is localized in a lattice site of the crystal. And there have been some measurements, some experiments in which they try to measure the non-classical rotational inertia that is proper of the superfluid. So the system is a solid that showed a bit of non-classical rotational inertia, so the supersolid. The problem with this system is that the condensate fraction were really, really small. So they are not really sure about the supersolidity in this system. So from 1970, there have been a lot of other attempts to try to imagine or investigate or observe this quite weird quantum state. One of the different approaches has been proposed in dipolar bosonic gas. So cold atoms, gases made of dipolar boson atoms. These in optical lattice. And essentially they try in two ways to probe this supersolid. The first one is they start from a condensate. So you have a macroscopic, a big condensate, and through optical traps, they reduce the interaction until you get a sort of density modulation of your initial superfluid. And then eventually, and this is what will be their supersolid, but then eventually if you reduce more the interaction between these, let's call it droplet, you will have separate droplets, so the system will be a crystal again. So from the superfluid to the supersolid to the crystal. The other approach instead was to start from a gas, first to form a crystal, and then through evaporative cooling to see if the cluster, the droplets of this system, could actually achieve a unique quantum state with phase coherence, so the supersolid. Now, this is a bit different from what I was telling you like few seconds ago. It's true that there is phase coherence in all the system. It's true that there is a sort of translational symmetry, but it's actually, we are talking actually more about the density modulation of a condensate. It's not the original idea of one particle per site. It's actually a cluster of particle, another cluster of particle, and another cluster of particle that eventually they all reach the same phase coherence. So there have been in the last few years some experimental evidence of this state, but as you can see, there are like different names, like dipolar quantum droplets, dipolar quantum gas metastable supersolid. So we are not still like completely in the first idea of supersolidity. So what we want to do in our case is to try to achieve the real idea, the initial idea of supersolidity. So how we want to do it? We want to use this system that is an electron-hole double layer system. So essentially you have a layer doped with electron, another layer doped with holes, and these two are separated by an insulating layer of thickness D, usually, in such a way that the electron and the hole, they don't tunnel. So they are well separated. And what happens in this system? We have Coulomb interaction, of course, between electron and hole. These are what we call indirect excitons. So it's a broad field that it's exploding now. So with indirect exciton, we mean spatially separated electron and hole. And actually, if you notice, the distance here can be very, very small. We are talking about nanometers. So these pairs are really compact. They are dipolar. And of course, at low temperature, why not? They behave like bosonic dipoles. So we are trying to use these as bosonic dipoles. Now, there have been a number of studies in this system. For example, you can have a double well of gallium arsenide. So you have a layer of gallium arsenide, another layer of gallium arsenide, and a barrier of aluminium gallium arsenide. This system, the thickness of this system is around 25 nanometers. Then you can reduce the distance, the dimension of the system. And for example, you can study the indirect excitons in double bilayer graphene. So you have a bilayer graphene with electron, a bilayer graphene with holes, an insulating layer, an insulating barrier that is usually boron nitride. And this system instead, we are talking about 2 or 3 nanometers. So you see the dimension already decrease. Then you can go also further. You can try with TMDs. So you have a layer of TMD, another layer of TMD. You can put a barrier, or in some cases, you can also avoid to put a barrier in the middle. So again, we are talking about a system that goes between around that is around 2 nanometers thick. Or another approach is to use similar to gallium arsenide, another system that is a bit more industrially scalable, that is the silicium germanium. And also in this case, we are in the order of 3-5 nanometers. So as you can see, there are plenty of possibilities and plenty of different thickness and setup. So you can play around with your system as much as you want to induce this indirect exciton. And what we really like about this system is that it's been already demonstrated from some experimental results that, for example, you can achieve Bose-Einstein condensation or superfluidity of this exciton. So indeed, this system, this exciton, they can behave at very low temperature as bosons. So because of this, we are really happy with this system. So if we get superfluidity, why not SUPERSOLIDITY? So a little bit of extra information on this system, because I would like to build up with you the phase diagram of this system to place our SUPERSOLID. The phase diagram of this system is really nice because you can actually build it with using just experimental parameters. So you can put on the y-axis the interlayer spacing that, as I showed you before, can be chosen as large as you want or as small as you want, depending on the system. You can tune the density in this system. So you can tune the electron and the hole density in this system, and you can put the interparticle distance, the characteristic length of the system, the separation between the particle, in the x-axis. And this will tell you where, like, some phases, some interesting phases will appear. Why? Because essentially there are two important forces that they act on this system. One is the interaction between the single carriers in one layer. So we have the electron-electron interaction, or the hole interaction, that of course goes like 1/R0 square. And we have the attraction between the electron and hole that goes like 1/D. So it depends on the distance. So for example, if you draw the diagonal, This tells us when these two forces are the same. But if you want to look at single particle phases, you are interested just on the phases of the electron or just on the phase of the hole, of course you will search in this space of parameter. Instead, if you're interested in electron-hole or exciton phases, you will look below this diagonal. Now, when you look below this diagonal, you have to take in account also another kind of force, that is the dipolar force, because we say that these pairs behave like a dipole. So actually you can understand how the force between this composite dipole is done, including all the components. So we have the Coulomb interaction, the Coulomb repulsion, and the Coulomb attraction. And you will get something that goes like this. And I will talk more about this force because it's really important. Now, all the length that you see are scaled with this AB. That is the effective Bohr radius that gives us some information about the radius of the exciton, and essentially depends on the mass of the electron, on the mass of the hole, on the dielectric constant that you want to put between the layer, or the dielectric constant between of the layers. So you can, again, changing the system, you change the parameter. So what have been done up to now? I told you already that a small interlayer distances, when the D is very, very small, there have been already experimental confirmation that because the attraction in this part of the phase diagram is much larger than the repulsion and is much larger than the exciton-exciton repulsion, what you get superfluidity or Bose-Einstein condensation of exciton. So the exciton superfluidity occupy this part of our phase diagram. Of course, we need to be careful because at a certain point, if we increase too much the density, then we are reducing the interparticle distance. The kinetic energy of the particle becomes really, really important. So the Fermi energy is also very important. And this kills the condensation. So this little green line that you see on the left of the phase diagram, it's where actually the exciton bound state collapse because of the screening. And with some calculation, we did this calculation in mean field theory, and we got this ratio that the superfluidity collapse more or less when the average of the interaction over the Fermi energy is around 17. So this is one of the first phase that I am talking about. Then let's try to increase a bit the D. Another phase that has been studied is the crystallization of exciton. This happens when the D is large, but is still a little bit less than R0. Now, that interaction that I showed you before, it's simply, in this limit goes to be, it's simply the dipolar repulsion. So it's telling us that in this region of the space, the two pairs, they really behave like a dipole. And again, if the dipolar repulsion is much stronger than the kinetic energy, so these dipoles, they remain fixed farther apart and they don't move. And this is the mechanism of a crystallization. So the dipoles are fixed at certain point in the crystal and they form their own crystal. Now, this transition from the liquid to the solid has been probed with Quantum Monte Carlo calculation. So there are some theoretical calculation that they show that the normal supersolid should occupy this space of the phase diagram. If we go farther, so we increase the distance between the layers, you see that now this distance is so large that actually becomes larger, the interparticle distance. So what really matters in the interaction between the particles of the same kind and not the attraction between electron and hole. And indeed, that interaction that I showed you before between exciton actually goes back to be a simple Coulomb interaction. But again, if you are in a region in which this repulsion is much stronger than the kinetic energy, then you have, again, crystallization. But in this case, you cannot talk anymore about crystallization of excitons. We have to talk about single particle crystallization, and this is the Wigner crystal. Also in this case, there have been a lot of studies already, both with mean field approximation and with Quantum Monte Carlo approximation. So we know that the Wigner crystal should occupy this part of the phase diagram. So, of course, you notice that there is a huge white area in the middle. Why? Because actually nobody was interested in this. Everyone was interested in superfluidity, so we tried to make it the system as thin as possible so that the electron and hole are really linked together. Or maybe you are interested to study the solid, so you want to do the dipole really large so that the dipolar repulsion is really strong. But nobody was interested in the middle. So what we actually are trying to understand is what is happening here in the middle. Is it possible that actually the phase coherence that it's proper of the superfluidity can resist up to higher distances between the layer? Or does the solidity kill the quantum phase coherence? In other words, is there an area in the middle of this white part of the phase diagram where we actually could see the supersolid of excitons? So this is what we are trying to get. And to study this, we started from a very simple approach, that is a variational approach. So we consider the dipolar Hamiltonian. You have the kinetic energy of your boson or our exciton, and then this is the interaction that I showed you before. So it's an interaction that accounts for the fact that there is repulsion between the single particles of the same carrier, and there is attraction between carriers of different charge. So in the limit of very small d, this will behave like a dipole interaction, dipole interaction. In the limit of very large d, it goes back to the Coulomb interaction. And now in a variational approach, we need our variational wave function. So we start using, for the superfluidity, an order parameter that it's normally in BEC, in Bose-Einstein condensation, is described in this way. So it's proportional to the square root of the density of the system. Then for the normal solid instead, so the solid of the exciton in the normal state, not the supersolid, we use a wave function that is actually a product of Gaussian. So every particle is centered under a Gaussian, and the Gaussian has sigma to sigma width. So this is the standard, another standard way to write the wave function of a solid. Then for the supersolid, what we do is actually we make a combination of these two. So we have a background component that allow the exchange, the jump between these Gaussian, so that it allows the phase coherence. And at the same time, we want one particle per lattice side, because remember that we are searching for the Chester supersolid. We don't want a modulation of this green order parameter. We want one particle per lattice side. So we put also some Gaussian. And of course, we have to take in account that these are particles that they should not interpenetrate to each other inside on top of each other. And this is done when we calculate the interaction in this way. I don't want to enter too much in details, but we account for the fact that there should be not overlap between the exciton. So with these three wave functions, we start to look at our minimal energy. So first of all, we compare the superfluid with the supersolid. So just remember that this is the phase diagram that we are searching. So in the supersolid, there are actually three variational parameters. One is the square root of rho SF, that background constant that I was talking about before. The other one is the spread of the Gaussian. And the third one is the square root of this rho SS, that actually is not an independent variational parameter because it's fixed by the normalization. So for example, if I choose rho SF equal to rho, then automatically rho SS will be equal 0. So I'm not talking about the wave function of the supersolid anymore, but this is degenerate with the superfluid wave function, so the energy are the same. We fix a density in such a way that we work a very low density. We want to start to work from the Daloid system, in the Daloid system. And we see what happens at 4 different value of D. And these are the results. I will show you slowly what is happening. So let's start with a very small d. So we are down here in our phase diagram. The dashed lines are the superfluid energies. So the superfluid energy is here. So you see at D equal 5, D over AB equal 5, it doesn't matter how I choose my rho SF in my supersolid order parameter, I will always get an energy higher, meaning that the ground state of this system is the superfluid. But what happens when I start to increase the D? So for example, I take this point in the phase diagram. Well, if I do the same calculation, I will discover that there is a finite range of rho SF value, and you see it better in this right figure, for which the energy of the supersolid is actually lower than the energy of the superfluid, suggesting me that the supersolid is the ground state in this system and not the superfluid. And you can increase more and more the distance between the layer, and you will see that the supersolid becomes more and more stable. So at this point, we are quite happy because we demonstrated that between the two in this white area, the supersolid is more stable than the superfluidity. So we will have superfluidity until a certain D, and then the supersolid will become the more stable. But of course, we need to compare now the supersolid also with the other phase that is the solid. So let's put the three phases together. We add the energy of the supersolid. So once again, we fix a density and we start with a small d. A small d, as I showed you before, the superfluid is the ground state with respect to the supersolid. The normal solid is way higher in energy. There is no way that in this phase space you will have a normal solid. So here is our superfluid, that is the stable ground state. Then we increase a bit the d. We increase the d, and as I showed you before, the supersolid becomes more stable than the superfluid. But the normal solid, that is this blue line, is still above these other two states. So this is our supersolid ground state. Again, we can increase a bit the d, and let's see what happens on top of the Quantum Monte Carlo predicted transition. Indeed, what we see is that the liquid normal solid, they have a transition. I mean, they touch each other. But what Quantum Monte Carlo didn't predict is that the supersolid is actually lower in energy with respect to these two. So here is still the supersolid that is the ground state. So the supersolid phase actually persists and preempt the transition predicted by Quantum Monte Carlo. Now, eventually we can increase D so much that we will see that now the normal solid energy will decrease so much that will become the lowest energy state also with respect to the super solid. So the normal solid of exciton is the ground state of our system. So this is for a fixed density. Let's draw a bit more clear figure. So there are two transitions. If I plot the energies of the normal solid, the supersolid, and the superfluid as a function of D, you will see two transitions that they describe the superfluid to supersolid transition, and then increasing D, the supersolid to normal solid transition. What we didn't expect was to see how important is to have that background component in our phase diagram. That was the ingredient that made the supersolid stable. Indeed, if you notice, there is no stability of the supersolid if this background component is zero. So to have a supersolid, we have to have necessarily the superfluid component, the superfluid background component larger than 0.25, for example. So it's really, being, of course, a variational approach, it's really important the choice of your variational wave function. And what we discover is the importance of the background component for the stability of this phase. So, of course, this was at a particular density. What we can do is to extend the calculation for all the density, so that now you will see our modified phase diagram with the supersolid that, as you notice, it occupies a very large, wide area of the phase diagram. It's what I want to remark again is that here what we are talking about and what we want to achieve, we wanted to achieve is that a Chester type of supersolid. So we have one exciton per supersolid site. And we discover that the superfluid component, the background component, is the essential ingredient to stabilize this supersolid. So we are talking about a supersolid without vacancies, without other stabilizing factors. And what really is exciting about this system is that you actually don't need all the trapping architecture that you need, for example, with cold atoms. Here you can change the length of the exciton dipole moment relative to the exciton spacing, simply changing the densities, the layer separation, the dielectric constant, the material. So you can stabilize the phases with respect to each other, changing experimentally controllable parameters. What is curious is also that we discovered that there is a triple point in this phase diagram. That, of course, means that a lot of other exciting things can happen here around if we start to include disorder, for example, or fluctuation. And so we really like this phase diagram, and we are going to investigate it a bit more. Now, this is a bit my conclusion, but I wanted to also make sure that I wanted to make more clear that what I presented to you today was a work done at 0 temperature. And this was a system in which we decide to tune the electron and the hole density equal, and the masses of the electron and the hole are the same. So, for example, we are talking of a system like graphene or TMD. But of course, there are extra challenges. For example, we want to extend this phase diagram, including unequal masses. Or, for example, we want to see how this phase diagram evolves at finite temperature. So with this, I would like to thank you for the attention. And if you are interested to know a bit more about this work, we have a preprint and archive with this work. Thank you very much.
Okay, so thank you very much for your presentation. And now I'm going to open the session here for questions and comments.
Mm-hmm.
So I don't know if you have already used this platform before, but what we do is we wait for the students or the audience to write comments on the YouTube chat, and then I will click on them and they will show up here in the screen for you. So
Okay.
but meanwhile, I can already make some questions here.
Yes.
So in the last phase diagram that you showed there is still a dotted line inside the exciton supersolid phase, the pink part of the phase diagram. I don't see your screen anymore. Okay, now I see it again. Okay, so there is a dotted line inside this pink region. What is there still something there, or?
No, this one was to actually to show the contrast with the Quantum Monte Carlo calculation. So this is the line that I show you in this slide. Okay. So this was the liquid-solid transition that was predicted by Quantum Monte Carlo. And this is to tell that actually our supersolid enters a bit inside the normal solid area as we expect. That's the issue.
Yep. And another question is, before they used to call this part that you are now painting in pink, it was this white part in the previous diagram, and they used to call it liquid, just liquid, right?
Yeah, because actually we don't know what is happening here. We know that the liquid in this part of the phase diagram, it's behaving like a superfluid. But then as you increase the distance between the layers, the particles, they feel less and less the attraction of each other. So the quantum coherence is can be stopped. It's killed, it's suppressed by the fact that the particles are farther apart. So actually it goes back to be a simple liquid, a normal state liquid. And then from the normal state liquid, what the Quantum Monte Carlo predict is that there is a transition to a normal state solid. What instead we claim is that there is actually the quantum coherence of the liquid survives up to very large distances between the layer, because it somehow is helped by the crystal order.
Okay, because that was my question. I see that, so in this phase diagram, the black line between superfluid and supersolid is already higher than normal, right? Or
yes. So these two black lines are calculated with that variational approach that I showed you before.
Yeah, because I was just curious about that, because it looks like you compared your solution to the superfluid solution and to the normal solid solution, but I didn't see a comparison with the normal liquid solution. And then it would look like there will be an extra phase in between there that will be a normal liquid also in this system, and that's why I got confused about it.
We don't compare it with the normal liquid because, I mean, the Quantum Monte Carlo already does this calculation, this comparison. So we know that between normal solid and normal liquid, this part under the dash line would be a normal liquid, but because they don't consider the possibility to have a supersolid.
Okay.
So in our case, this is a liquid that behave like a solid. It's a superfluid that behave like a solid, so it's a supersolid.
Okay. And this is also different from what I have been working on here. I have some PhD students now, 2 PhD students working on this problem too. But we have been working on a Gross-Pitayevsky approach. So we have a Gross-Pitayevsky equation with a wave function there, and then when you solve it, you get a density. So with that kind of solution, we get a modulation of the density. But I think that I would say that we will never be able to get what you get, because what you get there is a microscopic solution. And what we have, the wave function that we have there, it will never reflect a single particle in a single place, like it will always be a wave that represents everything. So it will be the same wave everywhere. So it's I cannot say that this is one particle and the other one is the next one. So this kind of Chester supersolid. So is that true that it's not going to be able? We are not going to be able to find a Chester supersolid exactly with this kind of approach, or?
Actually, what we are using here as a wave function is not a multi-particle wave function for the supersolid.
Yeah.
If you look at the wave function, it's an order parameter that depends just on one single variable, because what we want is a wave function that describes every one of these particles at the same way, because otherwise you don't have of diagonal long range order. So you have to have a single wave function, otherwise you don't have of diagonal long range order. And then
so then what would be a comparison between the Bose-Einstein condensate method and this one would be just maybe the radius of each of these of the droplets, I think.
You have to normalize the droplets in such a way that they have inside one particle per Gaussian, let's say.
Yeah. Okay. And let me see if I have more questions then. For the moment, the students still didn't write anything. So, so then in your calculation, you have a potential that is simply the dipole-dipole interaction potential, right?
It's similar to the dipole interaction. It's actually it evolves with the distance between the layers. It's this is the interaction that I'm using, and when you are a very small d, the interaction is exactly a dipole interaction. But when you start to increase the d, the Coulomb part of the repulsion start to take over, so it becomes more important.
Yeah. So because my question is because in the previous papers that I read about this problem of solids or supersolids, they claim that you can only get a supersolid if you have a non-monotonic interaction potential. So, for example, if you have a dipolar gas, then you need to have a kind of a head-to-tail interaction so that you get an attractive part on top of the dipole part. So that thing comes naturally in what you do, or?
This is quite interesting question, because that attraction that you are talking about in the dipolar atoms is the one that creates the clusters. So,
exactly.
for example, like this picture that you see, you have a repulsion between the dipoles, but in each cluster, you have an attraction between the dipoles, the dipolar atoms.
Yeah.
This is what create in quantum gases, in cold atom gases, what create the quantum droplets. But in our case, and it's a bit like an advantage in this case, if you want really to achieve the Chester supersolid, you will never have a situation like this. The exciton, they don't cluster because, as you say, there is no such attraction between the particles, between dipole. It's only repulsion. So the only thing that could happen in this case is a Chester supersolid. You will have an exciton separated by another exciton, separated by another exciton. You will not have a cluster. Maybe you can have a modulation of your supersolid, in the sense that you can overimpose a periodic modulation on your fluid of exciton, but you will never have a spontaneous formation of cluster like you have in cold atoms.
Yeah. Because that, and then one last question, and that's still related to that. So you do that, they form a solid, but you don't have also a kind of a bowl-like potential as you do there, because now they want to repel each other. They could repel forever, right? So once they put a parabolic potential, like a paraboloid, around the system, then the particles should be always repulsive. They should repel forever. But now they are bound by a finite size system. So that's why they form sometimes. This is what explains, for example, the Abrikosov solution of superconductivity, right? These Abrikosov vortices. But in your case, you have an infinite system. They are only repelling, but they still form, or do you have some kind of bowl holding the particles together?
Nope, they are purely repulsive.
Okay.
So that is one of the reasons why we like the system to try to prove the Chester supersolid, because they are just repelling each other. There is no way to cluster or to form droplets.
Okay. So let me see if there is any question from the students. Alguma pergunta dos estudantes? Vou dar mais uns 30 segundos para vocês escreverem, então. So give them 30 seconds to write questions in the chat if they want. Okay, then. So it seems like there are no questions from the students. So I will just thank you again for the very nice talk. So it's going to be available now on YouTube too. So if other students or other people interested in the topic want to watch it, you can just go to to our YouTube channel and look at it. So then Mateus is saying a great presentation and is congratulating you. Okay, so Giovanni is also, he actually wrote in Portuguese, but is just saying that it's a great presentation, has no questions for the moment. So, okay, so thank you very much. I'm gonna finish the live now. Then, so see you next Friday then. So thank you very much. See you maybe by the end of the year, right?
Maybe.
Okay.
Bye. Bye.
Até mais, pessoal.